My name is Anil Mankar, and I'm co-founder and chief development officer at BrainChip Inc. Today, I'm going to talk about Akida, our event domain neural processor, which is designed specifically for running AI at the edge IoT devices in very low power mode. Our name, BrainChip, gives it away. We design chips that mimic brain. And we take our inspiration from biology, but we have designed something which is completely digital. Today, I'm going to talk about the event-based architecture of Akida technology. What are the advantages of taking the AI inference into event domain? Also, I'm going to talk about our first product based on Akida technology, which is the AKD 1000. It's a neural system on a chip. We call it NSOC. And also Akida IP that is available for people to take our IP and embed into their own SoC for edge IoT AI application. I'm also going to give examples of neural networks that take advantage of event domain neural processing. And these examples actually, the network can see, they can hear like audio, they can really test, they can smell, and they can touch and feel. So all the five senses can be covered by very efficient neural networks that are designed to take advantage of event domain processing. And also, I will actually show you some of the live demos of this network that we are designed running on our chip in the demo section of this presentation.
You mentioned earlier on that it was an event-driven neural processor.
Right.
I guess I'm not familiar with event-driven deep learning types of neural nets. How do those work? I mean, is it just an inference engine? Is that what you'd call it?
No. So what actually happens is event domain means spike. So if you think about biology, our brain works on electrochemical pulses, and each of the neurons are connected to thousands of synapses, and the input, like your eye or ear, the compute element is same. And what happens is it does a spatio-temporal integration of the spikes. What that means is number of spikes came in a given time, how fast they came, and the information is coded into the nothing but spikes. So these are very small. Actually, they look like spikes if you really see the brain. And now what we do is our brain, when it processes whether there is information coming from the eye, for the ear, for the touch, the computing element is same. It actually does integration of the spikes over time, and whichever spikes are coming, there's a pattern in those spikes, and it picks up on those, and it actually learns from the pattern. And I'll go into more details as we go forward. But it's called spiking neural networks compared to people who are just doing mathematical approximation of a deep neural network, which is just nothing but taking lots of data and curve fitting it with the data that's given.
So you're doing a digital simulation of real spiking neural logic versus having just deep learning, with weights and all that other stuff.
Perfect, exactly. We do have weights, but those are kind of neural weights, and I'll show you an architecture that exactly does that. What we are doing is, while everybody looks at the deep learning problem as a mathematical problem, like you got hundreds, thousands of samples, and you're trying to curve fit for its statistical analysis of one of the 10 objects. If you're doing 10 object classification, you're just trying to see best possible weights, but it's all treated as a matrix multiplication. That's not how brain does. Actually, if a brain had to do mathematical calculation, nobody will be trying eggs on your head, But brain does that in 20 watts, what people are doing in Google GP or NVIDIA chips and things like that. So it's really amazing. The more we studied the brain, we started looking at the brain computation, and we realized that it doesn't make sense to really treat it as a mathematical problem. Just see what, with a basic fundamental belief that nature must be very efficient. So if you just mimic the brain and try to do the same computation, it must be low power. And that was, after 7 years of working on this technology, we have something proof that is actually right.
Would you call your system a neuromorphic solution?
It is neuromorphic, yes. It is a neuromorphic solution, just like IBM True North or Intel Lohi.
Right. Okay, thank you very much.
Yeah. So at the edge, and that's what happens. Because you're very low power, you can actually solve the analytic problem in the device itself. Now in the device, whatever sensor you're taking, you have to process it real time, but actually it has to fit in the low power budget of the IoT device. Also, when you're doing, in those small devices that are next to the sensor, There's not much of memory or memory bandwidth. The CPU is very low power. So you want to offload this computation as much as possible. And when people take neural network that have been trained in the cloud and you try to deploy it on an IoT device, if the environment changes, you might find a couple of new objects that you want to add. It'll be nice to train the device in the field itself, change according to the environment. You don't have to go back to the cloud and do all the statistical analysis of changing all the weights, which is what people do now. It'll be nice to have some learning or some rapid deployment at the edge. Actually, going to neuromorphic architecture actually gives solutions to all of those problems. The first thing is when you do neuromorphic processing, it means event-based. So only when events happen, you do computation. No events, no computation. Similarly, you want to reduce the amount of memory, fit into the memory that might be available. So we actually have all the inferences are done at 8-bit. Typically, clouds training is at 30-bit floating point or 16-bit floating point. There are different formats. But when people want to do a deep learning acceleration, which is like a Mac multiplier, similar things, they go up to, for inference, they go to 8-bit. We actually figured out that you can go further down to 1, 2, or 4 bits and fit into the memory capacity and the memory bandwidth that is available in the edge device. Now, because we do all this computation in the event domain, we actually mimic how our brain learns. It's called, there's an algorithm that brain learns by finding repeating patterns. We actually use something similar in digital domain, and we have one-shot learning. With just one object, you can learn something new, and I'll show you that in our demo when we show that. So it's really the neuromorphic. So we actually started from a clean slate saying, let's first study what the brain does and then try to mimic it. And by the way, I don't think anybody understands how a human brain works. It's much more complex. We have just taken the first step in just trying to do computation the way it is. There's lots of hierarchical layer, cortical columns and things like that. It will take us another 100 years to really figure out how human brain is so efficient to do something in 20 watts. But that's beside the point. So what we do is we actually took some principles from neuromorphic computing. But first thing is distributed computation. If you look at our brain, there are 88 billion neurons and 100 trillion synapses. But each of the neuron has its own memory for the computation, and they compute it independently. We do something similar. We actually distribute the computation over multiple NPUs, a neural processing unit. They have their own memory and own compute engine, so they can process events. The event-based processing, like I said before, it actually does allow us to reduce a lot of number of computation. And also, so what we do is when you do a inference engine, you get activation map. We actually treat the non-zero values in the activation map as 1, 2, or 4-bit values and do computation on that. But if their activation map has zeros, no computation required. The third thing that happens is as the neural processing units are using event domain processing, they take input or set of events coming into the input, process them, decide where there should be a spike that should be communicated to the next layer. They actually communicate over their own mesh network, so you don't really need a CPU to really communicate between layers of a network. Typical deep learning accelerators, which are matrix multiplication, do process one layer at a time. They actually save all the values they got after processing one layer. Then they go on to the next layer. Here, because we are distributing computation, multiple layers of a network can be distributed over whatever available number of NPUs available, and they will communicate the events over a mesh network without having need of a CPU. And the actual network that runs on the hardware is actually configurable at one time. So today you could be on the same hardware, you could be running an audio network or a vision network later on, or a LiDAR network, or a smell, the somatosensory network. All of those things, the configuration of the connectivity between neurons is changed. You load the weights and you run that. So it's really configuration of the network you run. It's really a processor. It's not designed for a specific network. It's really designed to process neural computation, and which network you run on it is configured. And because, again, because we do it in an event domain, we actually have a learning algorithm that learns from repeating events or spikes coming in. So you avoid your going back to the cloud to add new objects. So those are the four basic principles on which Akida IP is designed. So we analyze quite a few networks. This is an example of a 3 networks. These are mobile net V1 that do image classification for 1,000 objects or 20 objects or even 2 objects, visual, wake word. We're going to show you a presence detection demo running on the chip. But what this has done is, by when you want to do inference on a given frame from a camera, after you do convolution, because you get at least 50% zero because of the non-linearity function that you do in activation maps. By using event-based processing, we actually, because we don't have to do computation for zeros, we at least get half the operations are reduced. And there are some techniques that can improve the activity regularization that reduces the operations further. So, like in the mobile net V1, which is doing visual record, you have to do only 25% of the operation that any other DLA will have to do. Of course, that will lead to better power savings. Go ahead.
When you're doing video and it's inference, so when you're streaming the video, you're not keeping the video at all, right? You're
we're not. We're not.
And you're just dumping the
exactly. Actually, what happens is we take a frame, you run the convolution on initially RGB. The output of that we convert into events. And only where the intensity might be changing or whatever changes are happening, those are captured and those are processed. So definitely, we don't look at it again. Yeah, you don't have to look at the video frame again.
Right. So if one chip finds an anomaly, I assume that in your mesh network, the anomaly is sent to the other processors.
Actually, we send the events, so I don't know what you mean by anomaly, but anomaly detection is something that you keep looking at the
for change.
For change, yeah, exactly. So the change is processed, and actually we'll talk about the anomaly detection in my ball bearing example that you can see. If the ball bearings are perfect, you'll see some kind of accelerometer reading. If they are not perfect, they are defect, you'll see a different reading. So you can use it for anomaly detection. And actually, you bring a good point that neuromorphic computing is one thing very efficient in finding anomalies in the input stream. Like if you wanted to, like our image by our eyes process it very well, because you'll be amazed at how when the image processing happens in a human eye. It only stores the differences between different faces. If I saw you today and we meet you tomorrow, it doesn't store all the frames. I mean, it's really differences between the different faces, and it's extremely efficient. So even domain neuromorphic processing is very good at finding different differences in different frames and keeping only those, processing those. And I'll give you an example of that in my vibration analysis network that we have.
I have a question for you about the chips themselves. So is it, when these are purpose-built chipsets, correct? Is there only one model that you're using for this, or do you have different models for different use cases?
So this is really a neural processor in that sense, okay? Like take a look at ARM CPU. Now ARM CPU can do processing. ARM CPU is not designed just to do Excel spreadsheets or word processing and things like that. That's why we call it a neural processing unit. The network that you run on the neural processing unit is agnostic to that. It's not designed for just processing video, or there's no different NPU for processing audio or radar or LiDAR. It's really doing the computation for the neural network that you have, and you can run any network. The same hardware I'm going to show you will be running a audio or a vision or a LiDAR or a radar or any other data. So it's really a computing element. It's almost like a DSP. The algorithms you run on it is agnostic to that. Our brain, by the way, you can actually rewire the brain and connect your input from your ears to your eyes, and people are able to see it for some changes different. So there's a lot of the neuroscience is learning a lot about our thing, but the basic compute element is exactly the same. It's nothing but integration of spikes and firing. There's a term called the neurons that fire together, learn together kind of thing. So they've just become, that's why practice makes a man perfect, right? Because you're practicing a lot of things. What you're doing is you're making those neurosynaptic connections stronger and stronger. And the brain doesn't think, by the way. Brain just all these neurons are firing, and you're walking. They get a lot of feedback and say, yeah, what you did last time is good. So yeah, so it is actually a pure neural processor, just like a CPU or a DSP. It doesn't matter what network you run on it.
One of the biggest challenges with neuromorphic chips has historically been the software tools to provide the the hyperparameters and the model structure, or the connectivity and that sort of thing. I mean, there's lots of tools available for, I'll call it, digital neural networks that exist today: Keras, TensorFlow, PyTorch, et cetera, et cetera. But there's very few system frameworks that I'm aware of specifically for neuromorphic types of architectures. What are you doing from a software perspective to make your hardware chip more usable?
Very good. You don't have to learn any new software. What we have done is actually, so while I have my network is neuromorphic computation, we have adapted the approach of using Google TensorFlow Keras and the same tools. So you don't have to, I'm taking your CNN, like MobileNet V1, actually example I'm showing you, is actually your CNN that you would do matrix multiplication on, but I convert those into an event domain. So I provide you hardware that will create events out of frames, also do the computation. So you don't have to program the neural network, and the tools we use are what you're familiar with. Of course, we have some Python, other thing for, and I'll show you how we encoded some of the event domain direct algorithms can be directly encoded, 1-bit weight and 1-bit things. But the tools that you're using for this operation are the tools that you're already familiar with. We actually hide all that under a runtime environment that programs the neural processor, loads the weight, run the inference, and give you results just like you would have run it on an NVIDIA GPU. That's the beauty of this architecture, that you don't have to learn something new. Now, of course, I know what you're talking about is IBM True North. You have to almost understand how to correlate. So those are designed for neuroscientists to experiment how brain behaves. Or even Intel Lohi actually has hundreds of parameters for mimicking brain to study Alzheimer's disease for the neuroscientists. Only neuroscientists know how to program it. What we have is, we have a product that's designed to solve today's problem, and we take a CNN take it into event domain and run the inference. Or there's a, if I'm getting, like we talked about camera frames, right? So if you give me a camera frames, I will create events out of it. But there are different type of cameras that actually generate the events directly. These are called dynamic vision sensor camera, DVS camera. They actually, rather than sending you 2 million pixels, they send you only the address of the pixel that change in intensity. Just like our eye, so these are called actually artificial retina. So there are devices like that. There's a device for cochlea that actually can generate spikes from a auditory things. These are actually silicon chips people have done. ETH Zurich has done those. We can take the inputs directly, events from those devices, and process them directly in the event domain.
So you're saying that I could take a normal convolutional neural network and just feed it into the BrainChip software, and it will convert it to an internal digital neural network, spiking neural network solution.
Yes.
Can I do that for other neural networks as well, like LSTM or any of the other RNN types of solutions?
So this is our first generation technology that we are doing first feed forward. Another thing, LSTM will actually, the neuron model we have right now is a integrated fire neuron model, so it doesn't have memory today. But our next generation we are designing, we actually adding memory states so we can do LSTM. Because LSTM, this is a sequential network, right? You have to store a lot of things.
Right.
So this is our first generation Akida 1.0. And we actually, our research team is looking at LSTM and things like that, and recurrent networks. But those are second stage. Right now, most of the things I'm showing you, like you can hear, you can see, you can smell, you can touch, and you can feel. All of those are first technology.
So essentially, any neural network that doesn't require memory or temporal understanding can be mimicked in this solution with this current tools. Is that?
Yes, we can, and we are working on the LSTM network for the next generation Akida.
Yeah. Okay, thank you very much.
Looking like 10 years forward, what kind of problems you see this kind of chip solving then?
So this is what we call, because you have to, by the way, so let me just, when people are talking about deep learning, accelerators and deep learning, what we call deep learning today, there is no learning, there's actually deep training. What you're doing is you're taking hundreds of thousands of samples And your curve fitting, what's the closest thing? A statistical thing. So nobody is learning, but neuromorphic architectures can actually learn from the repeating patterns. Like let me give you an example. If a child sees a dog all the time, but his mother tells him he's associating what he saw with what he heard, and if the mother told him it's a cat, he will learn to recognize that as a cat. So it's learning by the learning is by just by experiencing the environment, all the five senses we have, and as the repeating that you see, we find repeating patterns. Now somebody has to label it, and I'll show you an example of our smell network, how we labeled it. So it's really, unless you go to a neuromorphic processor, you cannot have artificial general intelligence or learn from the environment. Deep training, or as we call it, is nothing but curve fitting and doing statistical things, saying it's probably one of those 10 objects it is, and there's a probability of where it falls. So that's the main difference. So unless, and this is what everybody has realized, and IBM and Intel has put in a lot of effort in trying to say next generation, it has to be spiking neural network. What we have done is we are slightly ahead of them in terms of trying to productize it to solve today's problem, which are CNN, but the same hardware, you can do a completely neuromorphic spiking neural network in the same hardware today with learning. And I have a couple of examples that I'll show you, which are neuromorphic algorithms implemented on the current chip. And of course, we'll be you're asking, yeah, we'll remember now, because what happens in our brain also, the first layer is just takes all the sensor data and creates a one layer. The higher level of cortical columns are actually finding features at a higher level and then associate the picture with the audio and with something else, and that's how it is actually recognized. So learning, you've got to go to neuromorphic. If you stay with matrix multiplication, you'll just be doing statistical analysis.
Out of curiosity, how do you compare to Lohi in the sense that they do about 130,000 neurons in a chip? So I'm wondering, how do you stack up to that?
Yeah, so they have Intel Lohi has 128 neurons and 100 million synapses equivalently. We actually do 1.2 million, 10 times more neuron if you only wanted to count a neuron to neuron, and 10 billion synapses with the memory that we have in 8 megabytes of memory and the hardware that we have. Intel has about 35 megabytes of memory to do 100 trillion synapses. And the difference is we actually have gone down to, because Intel allows you to go up to 12 bits for synaptic weights. We stick to 1 to 2 bits because it's good enough. So really we designed it to be a product commercialized now because we are a small company. We don't have funds like Intel. But Intel can really have a research. Intel thing is more designed for research neuroscientists to study brain and they probably have 25 or 30 different ways of learning. We picked one learning way which we needed, and we implemented that.
Intel, they formed this whole INRC initiative, and they try to go after the enterprise and edge market. So they are kind of pulling back on what they're trying to do. So when a big company such as Intel is not able to make an impact, what success do you think you're going to have as a startup?
So we don't. So by the way, so when you mean by enterprising is basically like Grok and NVIDIA GPU. So Intel has two different markets. One is going after the NVIDIA GPU market for the in the cloud inference or training, and the second thing is IoT. The IoT, I don't think anybody has a very good solution yet that can fit into the power, computation, other thing requirement that I talked about in edge IoT. You just want to be next to the sensor, and instead of sending so much data to the cloud and let it get analyzed in the cloud, you want to make the sensor smart. Because if you today in a Tesla car, you have 8 or 9 cameras that are sending full definition videos and all that goes onto a big box, and now you're doing video analytics. Why do you have to do that? We can actually look at every frame and really see that, okay, I'm looking for these 10 objects. If I don't see the object in the frame, let me not send it to that. So that's the kind of information. So what we are saying is we actually purposely decided to design something that can be commercialized for the edge IoT device, which is small enough, low power enough, and we are focused on that. Of course, Intel is a big company. They have actually made public statements saying the first step for them is for research guys, and once the algorithms come into spiking neural domain, they will commercialize it. And they themselves say that if this is for research and a couple of places where I presented my technology, Mark Davis says, if you want to commercialize something now, talk to BrainChip, or if you want to do some lot of research, use Intel Lohi. And think about the other one is, it doesn't matter to the IoT device what technology you use to solve the problem. If I can do, let's say 5 frames per second, or I can detect keyword in a low power budget, and it fits in whether you use a matrix multiplication or neuromorphic computing. We just believe that neuromorphic computing inherently gives us the low power advantage, low size, and all that. That's why we focus on that. And you'll wait for my demos to see, and I'll show you the same application that people are solving. We're trying to do matrix multiplication. We solve them very efficiently with the neuromorphic computing. So hold your thought for a little bit till I show you the demo. So second thing that we did, because definitely memory bandwidth and memory capacity is a problem. So we did a lot of research and analyzing a lot of papers that said 4-bit inference might be good enough. And don't be afraid of going down below 8-bit. What we did is we actually analyzed quite a few popular neural networks. These are like Google speech command. It looks for a keyword like Hey Siri or OK Google. A visual wake word says, is there a person in the frame? Or you can do ImageNet 1000, and that can be classify 1000 objects. If you go from a 32-bit floating point to a 4-bit activation and 4-bit weights, these are the results of the accuracy of the network running at 4-bit. Yeah, you can lose 1 or 2% depending on the data set and the problem that we are trying to solve. But the power advantage of going to 4 bits, power advantage of doing it event domain is huge compared to the accuracy drop that you might lose. And these are the standard benchmark. When in your application, you might actually be okay with the accuracy drop that we are seeing here, like a visual wake word. It goes from 90.7% to 89.7. It still detects a person, and it's very low power. So you could deploy that. So what we have done is, because we decided to go to neuromorphic computing and event domain, every problem that CNN that you have, we can solve those. But we reduce the operations and reduce the memory at almost the same accuracy. But we are moving those problems to the left to take advantage of the low power nature. These are all the standard networks. Somebody was asking me, can I take a CNN? Yes, you can take the CNN. These are all been analyzed, popular things that you want to run, just take an image and look for a visual record, or DVS camera, which is native neuromorphic things. We actually do very good with 3D point cloud. LiDAR or some other gesture, our partner Magic Eye has generated 3D point cloud from an image for 3D depth sensing, or resistance time series, just values for olfactory smell detection, or even ball bearing fault detection. All of these analyses, look at the activation sparsity that I talked about. Some of these networks go from 30% sparsity to 90% sparsity. So if the sparsity is more, less computation, less power, these are very good examples of standard network that you want to run, and they can actually fit on the device that you want. These are slightly medium and large size networks, but then still again, you'll be able to do it on the device that you want to do in the budget that you have.